In this video, we're gonna start section 1.4 on factoring. Our goals for this section are to review how we factor expressions with two terms. Those will involve using some common formulas. Three terms, often those are gonna be things like quadratics, and factoring things with four or more terms. And to do that, we'll use grouping. We'll talk about how we can recognize when we factor something by substituting. And we will end by discussing how we simplify what are called rational expressions. Okay, so in this video, I'm going to talk about some common factoring formulas and then also discuss how we can factor expressions that have two terms. Okay, all right, so let's get into some factoring formulas. So first, difference of squares. If I have something of the form x squared minus y squared, so this factors is x minus y times x plus y. So that's our difference of squares. A difference of cubes, if I have something cubed minus something cubed, that also factors. It starts off in the same sort of way as x minus y, but the thing in the second parentheses is a bit more complicated. It turns out we get x squared plus xy plus y squared. We've actually seen this first formula before when we talked about conjugates. With the difference of cubes factoring formula, we could check this if we wanted to. Like we'd have to kind of FOIL it out, like multiply x times this term, and then times this term, and then times this term, and then do the same thing with y, multiply by that, and then by this, and by this. It'll turn out a bunch of things will cancel, and you'll end up with just the x cubed minus y cubed. I won't work that out, but that might be a good thing to practice on your own and just verify that those are actually equal. Okay. So a sum of cubes, x cubed plus y cubed, also factors. In fact, there's a very quick way I can get the sum of cubes factored formula if I know difference of cubes first. To get sum of cubes, all I got to do is replace the y in the first one with a negative y. Because if I were to replace this y with a negative y, I'd get x cubed minus, and then I'd get negative y cubed. But when I cube the negative, it stays negative. And then this other negative in front turns it into a positive. So I would end up getting x cubed plus y cubed. So it would turn into a sum of cubes. Okay, so I'm also going to do that on the other side of the formula. Anywhere there's a y, I'm going to replace it with negative y. Okay, so I'll have x, and then this y changes to a negative y, and with this other negative in front, it'll change it to a positive. So I'll get x plus y. In the second parentheses, I'll have x squared, and then I'll have x times, this will be a negative y, and that'll give me minus xy. When I put minus y into here, when it gets squared, the negative goes away. So I'll still have plus y squared. So overall, it ends up being kind of essentially very close to the formula I had for difference of cubes, but just two of the signs end up changing when I change that y to a negative y. Okay. And then finally, sum of squares. If I have x squared plus y squared, this one, a bit of a trick question. It turns out this one does not factor. So sum of squares does not factor. Okay. So eventually, we're going to use these formulas so much, hopefully, that you'll end up having all of them memorized. At this point, I would kind of expect that you're fairly comfortable with this one. At least that you would have seen this a bunch at some point in algebra. The other ones you've probably seen, but maybe have used a bit less. Okay, all right, so let's get into factoring two-term expressions. So the steps for this are, first, you factor the common terms, if there are any. And then the second step is, well, once you've done that, use one of these common formulas, if possible. Okay, so I want to do this example first here. Example 0, factor this expression. So I want to notice first that, well, these two terms, well, they have an x squared in common. So I'm going to factor that out. So if I take out x squared, what I'll be left with is x to the third from the first term, and then minus 6 from the second term. Okay, so that's how it factors. If I wanted to check this work, what I would do is I would distribute the x squared into both of those terms. And if I did that, I should get back the original. Okay, and it turns out I will. Okay, all right. So what I want to do now is use this to kind of tackle a harder example. I want to factor something. I want to factor something where I got some negative exponents. Actually, maybe one thing I should have mentioned about the previous problem is, well, when I did take out that x squared, could this thing in parentheses have been factored further? It turns out no, but why? Like I have this x cubed here, which might make me think of one of my cubes formulas. I have a minus sign, so maybe I'm thinking difference of cubes, but unfortunately the 6 isn't a perfect cube like 1 or 8 or 27. So I can't use difference of cubes so nicely to factor that. So that's about as far as I can go. All right, so returning to this next example, I want to factor this thing. It's got some negative exponents. How can I factor when I have negative exponents? I'm actually going to use this previous example with positive exponents to help motivate the idea. So what's going on when I actually factor out the x squared? Well, when I do that, what I end up with is this first term, x to the 5, gets divided by what I just factored out, the x squared. Same thing with the next term. I have minus 6x squared. That gets divided by what I'm factoring out. And if I just kind of test this now, what does this simplify to? When I do x5 over x squared, well, that's x cubed. This next fraction, the x squareds cancel, and I just get 6. And of course, that minus sign. And that's the same thing that I have here. So this idea where whatever I'm factoring out, that divides each of the terms, and that's what's left over in the parentheses. I'm going to keep that in mind, especially when I have negative exponent terms. Okay, so let's start this next one off in the same way. Let's identify the common factors. Well, I see a 5 is common to the 15 and the 25. And then I see both the terms have some x's, and I want to factor out the smaller power, which is x squared. They both have some y terms, so I also want to factor out y to the smaller power, but the smaller power is negative 5. Right, because negative 5 is smaller than negative 3. It's more negative. Okay, then I start a parentheses, and then I'll write the leftovers. Okay, so for the leftovers, if I take a 5 out of 15, I'm left with 3. If I took out 2 x's, which means I'm left with 4 of them, and then I took out all of these y terms, so there's no y's left over. So that one wasn't too bad. The next one is a bit trickier. So if I factor out a 5 from the negative 25, I'm left with minus 5. I took out all the x's, so there's none of them. But what am I going to have with y? This is where I'm going to use this idea from before. The way I can do it is I'll write what I have currently, which is y to the negative 3, and then I'll divide it by what I just factored out. The y term I factored out was y to the negative 5. Okay, and then I'm going to simplify it. So when I simplify this, y to a power divided by y to a power means I subtract the powers. I'll get y to the negative 3 minus negative 5. So double negative becomes a positive. Okay, so that becomes y squared. Okay, so I end up getting 5x squared. Let's make all these negative exponents positive. Let's move that to the denominator. So over y to the 5th. And then parentheses, I got 3x to the 4. And now I got minus 5y squared. Okay, it's worth asking, the thing that's in parentheses, this thing that's left over, can that be factored further using squares or cubes? I see a square here. Even x to the 4 is technically a perfect square, but unfortunately 3 and the 5 are not perfect squares. So I can't take this any further. Cool, so this would be my answer. This is as far as I can factor this. If I had wanted to, I could have taken these negative exponent terms and moved them to the denominator at the beginning and then tried to get a common denominator. That definitely works as well. I think it's a little bit longer, personally, if I feel good about factoring out these negative exponent terms, which, we are practicing through this example. Okay, let's tackle another example. Okay, so next one. So I got this long-looking expression. So the first thing I want to observe about this is when things are being multiplied, like 18 is multiplying this whole thing in parentheses, that's multiplying this whole thing in parentheses, all of that is considered one term. And then when there's a subtraction or an addition after a term, that separates terms. And then after that, I have something multiplying this parentheses, multiplying that parentheses. So all of that is a second term. So overall, I technically have a two-term expression. Okay, so let's factor out any common terms. So from the 18 and the 8, I see that 2 is common. I see both of these have these negative 2x plus 1. So I can take out that to the smaller power, which is 3. They both have an 8 plus 3x. Again, I factor out the smaller power, which is 5. Just because this one's long, this one with the leftovers, I'm going to put them in brackets. I could definitely write parentheses if I wanted to, just personal preference. Because I notice it's long, sometimes it's nice to write brackets for the leftovers. Okay, what's left over from the first term when I took all this out? Well, dividing the 18 by 2, I'm left with 9. I'll have one of these negative 2x plus 1s left over. Because there's just 1, I don't really need to write the exponent 1. I could just write it without it. And then I took out all these 8 plus 3x's, so I don't need to write that. So I'll move on to the next term. From the next term, with the negative 8, when I took out this 2, I'd be left with minus 4. And then, well, I'll be left with an 8 plus 3x. There were 6 of them. I took out 5, so there's just 1 left over. And then I took out all 3 of these negative 2x plus 1s from that second term. So these are all the leftovers now from that second term. Cool. Okay, so let's now simplify all of these leftovers. So I can distribute in the 9 and get negative 18x plus 9. I can distribute the negative 4 and get minus 32 minus 12x. And then simplifying that, I get minus 30x. And then plus 9 minus 32, that's negative 23. Okay, so writing all of this, I have in the front 2 times negative 2x plus 1 cubed times 8 plus 3x to the 5. And then my final leftovers, now I'll switch it to a parentheses, but I could leave it in a bracket if I wanted to, minus 30x minus 23. Okay, and the stuff in this parentheses, it can't really be factored more. There's nothing else, no other common things I can take out. It's not a difference of squares or perfect cubes. This is as far as I can take it. Okay, so far I've been kind of slowly ramping up the difficulty on some of these two-term expressions, and I haven't really done an example where I've used any of the common formulas. Okay, all right, let's do a few more examples. Okay, next one, 16x squared minus 25y to the 6. Okay, so which of the formulas seems like... Well, so first I want to ask myself, are there any common terms? Well, with the 16 and the 25, there's nothing common. The first term has some x's, the second one has some y's, but nothing's common there. So no common terms to take out. So now I think about, can I use one of my common formulas? So do I either have some perfect squares or some perfect cubes here? In seeing these exponents, I'm thinking we got maybe some perfect squares. So I'm going to try to write this as something squared minus something squared. And I'll think about what goes in the parentheses. So what squared ends up equaling 16x to the 2? Well, I'll need a 4 to get the 16, and then I'll need an x, so that when I square it, I get x to the 2. Cool. Next parentheses, I'll need a 5 to get the 25 when I square it. And for the y, I'll need y cubed. Because when I square it, the power to a power, they multiply, and I'll get that 6. Okay, so I get to use my difference of squares, which says, oh, when I factor it, I'll get something minus something, and then times something plus something. It's the first thing that's getting squared first, and then minus the second thing that's getting squared after that, so minus 5y cubed. And then similarly in the next parentheses, 4x, and then plus 5y cubed. Awesome, so I did a difference of squares there. And I should technically ask myself now, can either this parentheses or the thing in this parentheses be factored further? Well, 4x isn't a perfect square, because because x is not a perfect square. It's not a perfect cube for sure. So I don't think there's anything more I can do with that. And similarly with this next parentheses term. So that's as far as I can take it. Okay, so I want to wrap up this video with one more example. Okay, so 27t to the 6 minus 8. Okay, so are there any common terms first? Well, with 27 and 8, nothing's really common. The first term has some t's, but the next one doesn't, so no common terms. So then I think, can I use one of my common factoring formulas? Is this some perfect squares or some perfect cubes? And this one looks like I might have some perfect cubes. So something cubed minus something cubed. Okay, so, well, what goes in the second parentheses? I think that's a little bit easier. What cubed is 8? Well, that's 2. In the first parentheses, what cubed is 27t to the 6? That's going to be 3 and then t squared. Okay, so I do have some perfect cubes here. So let's just remind ourselves, well, what's the difference of cubes formula? So if I have x cubed minus y cubed, just kind of copying it from up above, difference of cubes says, well, that factor is x minus y, parentheses, times x squared plus xy plus y squared. Cool. All right, so let me zoom in and use this now with the terms that we have. So I have this difference of cubes. I'm going to get to write it as, my first parentheses times my second. And essentially anywhere I see x in this formula, I'm going to be plugging in this first thing that's getting cubed, that 3t squared. And anywhere I see a y in the formula, I'm going to be plugging in the 2. That's the second thing that's getting cubed. Okay, so that's going to give me 3t squared minus 2, and then x squared, which is, well, it's 3t squared, that whole thing in parentheses getting squared, plus x times y, so that's 3t squared times 2, plus y squared, so that's going to be plus 2 squared. Okay, and then I think I can simplify this second parentheses a bit. The first parentheses stays as 3t squared minus 2. The second one, well, when I square this first term, I'll get 9t to the 4th. Multiplying the next one, I'll get 6t squared. And then finally, plus 4. Okay. It turns out that when you do either difference of cubes or sum of cubes, it turns out the thing in this second parentheses with the 3 terms pretty much never factors more. So I don't really need to bother thinking about that. The thing in the first parentheses, sometimes can factor more, so I should kind of think about that. Seeing the t squared makes me think of maybe some difference of squares, but unfortunately 3 is not a perfect square, and neither is 2, so I won't have a nice difference of squares here. This is as far as I can take it.